Thank you all for coming. I'm sorry my voice is a little hoarse. It's about 5 o'clock in the morning for me, so any mistakes I make are due to jet lag. So first I want to thank the organizers, Denis, who's not here right now, Mohammed, Stefan, Stefan the First, and Anlor. Thank you. And I hope they don't have any control over this thing. If I do something wrong, they'll shock me or something. We'll see. So it's nice to be here. It's always a pleasure to be here in France. It's particularly nice now. The winter has been cold in Washington this year, unusually, with a lot of snow, and it's particularly good to get out of Washington in this year, which is an election year in the United States, where really crazy things are going on. But we won't talk about politics. So what I want to talk about today is some joint work with my colleague Tunjai Alparslan, and it'll be about some stable distributions, but there's a direct analog extension to max stable distributions, which I'll mention at the end. So here's a quick overview. We're going to talk just briefly review some ideas, basic definitions of multivariate stables, distributions, and we'll define this dependence measure, which I called eta, mainly because I couldn't think of any other symbol to use. And it depends on a parameter p. Then a sample analog of that, eta hat, and then some topics at the end if we have time. So if we say a random vector is stable, and I'll use this description here. There's alpha, an index of stability. There's this lambda, which is the spectral or angular measure on the unit sphere. And then there's a shift parameter. And I don't want to dwell on this, but there are multiple parameterizations possible. I'll just briefly mention the two of them. But basically, the joint characteristic function has this representation. We have an exponential here, minus an integral. So you integrate over the sphere in d dimensions, this kernel function against the angular measure. And then there's a shift vector over here. But how you choose this kernel vector here, so this middle one is the one parameterization when j equals 1. This is the one that's most common. It's a little bit easier to prove things with it, but it's discontinuous in the parameter alpha. This expression blows up as alpha goes to 1, obviously. Whereas if you make this definition up here, you get a continuous parameterization. So there's alpha, as alpha varies over the whole range, things vary continuously. So when I do some estimation, I'll use the zero parameterization because you avoid some problems with the discontinuity there. Okay, so another way of describing that's not as well known, although it's implicit in many of the proofs with some stable, multivariate, some stable distributions, is the fact that if I take a vector u and I take the inner product, that is, so I take this linear combination, so I think of u as a direction, and I'm taking a linear combination, so I'm projecting in the direction u. That if I do this, that I get a univariate stable distribution. So there's a constant index of stability alpha, and for a particular direction, I have univariate parameters beta, which depends on the direction, the scale gamma, which depends on the direction, and the shift vector depends on the direction. So we call these functions the projection parameter functions, and they completely determine the joint distribution via the Cramer-Wold device. So we can actually parameterize the multivariate stable distribution by this index of stability. And instead of using the angular measure, you combine these two. The skewness function and the scale function are equivalent to knowing the angular measure. And at least in this section, we're just going to focus on 2 dimensions and that we have normalized components. So the scale in the x direction is the same as the scale in the y direction as 1. And sometimes it'll be useful to use polar notation if I want to, particularly if I want to look at the scale around the unit circle. I'll denote gamma of theta to be the scale in the direction cosine theta, sine theta. Okay, so here's some pictures. Very simple. Here's a way to try to think of representing an independent. So here's the angular measure over here, which is, in the independent case, you have all the mass as point masses concentrated at the North Pole, South Pole, East Pole, West Pole. On the unit axis, all the mass is concentrated there. And the scale function looks like this. If you take a uniform measure on the unit circle, you get a uniform, an isotropic distribution, and its scale function is identically 1, like that. So basically what is useful in certain problems is, you can think of it in either way, but for what I'm going to do here, it's easier, for me at least, to think over on the right-hand side here using the scale function rather than the measure. So if I take exact positive linear dependence, I put all the mass on the diagonal line, and you get a scale function that looks like this. Again, we've always, remind you, we've normalized so that the scale is always 1 at the 4 north, south, east, west poles. If you have all the mass in the first quadrant, you have positive association, and the scale function looks like that. Okay, so that's all review. But what I'm really going to propose here is that for our purposes here, rather than try to estimate the spectral measure, which we generally don't have any idea what kind of measure it is, it could be discrete, it could be continuous, it could be a mix, it could be whatever, is we're just going to look at the scale function. So here's the idea. The independent case, so this little gamma with a perpendicular symbol here is going to stand for the independent case. The scale function is very simple form. It looks like this. So when there's a subscript with a perpendicular symbol, it means we have an independent scale function. And all I'm going to do is look at the distance. So here's the picture, shows it to you. And in this case, this middle curve here is the independence case. If I have some other distribution with its scale function like that, I'm going to basically look at the LP difference between those two. So it's very simple. If P is 1, you're just looking at the area of the shaded region here. Okay, so some properties. Why this is interesting is because X has independent components if and only if this eta quantity is 0. And can you do it for any value of P? Later on, we'll focus on P equals 2 just because maybe the critical values are a little easier. So alpha can be any value in 0, 2. So in particular, if you're used to, say, the covariation for a stable random vector, it only makes sense if alpha is greater than 1. This quantity makes sense for any alpha. In 0, 2, it can have symmetric or non-symmetric components. It can be centered or shifted. It's only focusing on the scale function. It's symmetric, obviously, because we're just talking about a distance here. I'm sorry, maybe it's not so obvious. It's symmetric because in the scale function for the independent case has this, it's the same in each quadrant. Okay, so if you interchange the components, you'll just shift where the scale functions differ. And this quantity, more than just measuring how far apart these scale functions are, it also tells you something about the density. So for example, if we have a symmetric distribution, then you can actually prove that the difference between the independent density, so this is the bivariate density for the independent case, this is the bivariate density for our general case with scale function gamma, that you can prove that the difference is uniformly small over the whole plane, and it's bounded by a constant multiple times this. So if the scale functions are close in some LP sense, then this should be a 1 here. There should be an L1 here. But you can do it in other senses too. Okay? So if the scale functions are close, then the densities have to be close. In the non-symmetric case, you need a little bit more than this. You need to know at least what the skewnesses are in the two components. But I think it'd be. Okay, so the P norm is evaluated as an integral over the unit circle, not over the whole plane. So it's numerically, it's a lot nicer because it's just an integral over a compact set. And you can write it in polar coordinates this way. You can put the 2 in here because everything is pi periodic. So rather than going around the whole circle, you can do half the circle multiplied by 2. So this quantity is always non-negative, so there is no concept of positive dependence or negative dependence in this sense. There's attempts to, and if you could look at, say, the covariation, there is an attempt to design, there is a definition of a signed covariation, but it's somewhat artificial. In some cases it makes sense, in some other cases it doesn't make any sense. I'll talk about that in a minute. But I'll just try to say that while this may be a little disappointing, I don't think there's any general way to put a sign dependence measure. So if you, for example, if you take the independent case, so you have point masses along the axes, and you rotate it pi over 4, all right? Is that positively dependent or negatively dependent? I don't think it's either. So I'm not sure you can assign a sign in that case, and in general, so we're going to live just with a positive measure. So 0 is, if it's close to 0, it's close to being independent. If it's far away from 0, then it's far away from being independent. The definition makes sense in the Gaussian case. When alpha equals 2, you can calculate the scale function, and then when you do this integral, you get that it's just a constant multiple times the absolute value of the correlation. In the elliptically contoured or sub-Gaussian case, you can get an integral expression. You can evaluate it numerically. So I should say this work just appeared in Extremes. It's online right now. The paper version will be coming out in a couple months, I guess. So I think there's a plot of this as you vary that dependence parameter in the elliptic case, what this eta measure looks like. And then if I have, going back to a d-dimensional case, you have mutually independent components if and only if all pairs are independent. So you can test for joint independence by looking at all pairwise eta measures. Okay, so I want to comment just a little bit. One of the things we also tried to do in this paper is look a little bit more at covariation and codifferences. So if you don't know it, here's the definition of covariation. Remember, you have this spectral measure or angular measure lambda on the unit circle. So the covariation is denoted by this symbol, and it's given by the integral of, so this S1 times S2, and this is the signed power. So you take the sine of S2 times the absolute value of S2 to that power. So you integrate that quantity over the unit circle, in this case. It can show that this is given by the partial derivative, well, 1 over alpha times the partial derivative of the scale function at the point u1 equals 0, u2 equals 1. So it's at one point. So this measure is only looking at the scale function in the neighborhood of that point. Okay, so it's not capturing what's going on everywhere. And that's why it doesn't capture independence. So if the components are independent, then the covariation is 0, but the converse is false. And here's a short diversion on when you can get covariation equals 0. Very simple arguments here. If I have an angular measure that's concentrated in the first and third quadrant, so QJ is the jth quadrant, then you have positive association, but you also get a positive covariation. If you put all the mass in the second and fourth quadrants, you have negative covariation. And then the covariation is linear in this angular measure, so if I take a positive linear combination of the two, I get the covariation of this measure is the linear combination of the covariances. And so by choosing, so I can take any measure with any kind of mass in the first and third quadrant, maybe continuous, some sort of continuous angular measure, and take any measure that has positive mass in the other two quadrants, say a discrete piece, so they can be very different pieces, and if I take the right constants there, I can get the covariation. Since one of these terms is positive and one's negative, if I take the right constants, I get 0. So I can have very, very different kinds of distributions having 0 covariation. And again, the real idea there, it's only looking at one point, one direction, so it can't capture everything. There's another concept called and I should have mentioned that the covariation is only defined for alpha bigger than 1. There's a codifference concept for bivariate stables. It's defined, the original definition is a little bit different, but you can define it easily in terms of the scale function. It says, look at the scale function in the x direction, add to it the value of the scale function in the y direction, and then look in the direction 1 minus 1. So look down in this direction and evaluate the scale function there, and take that sum. This makes sense for any alpha between 0 and 2. And again, you get the 0 if the terms are independent, but it's not characterizing independence. And you can do the same kind of thing we did on the previous page, at least for alpha bigger than 1. You can construct things that are, if you put mass in the first and third quadrant, you always get a positive codifference. And you put mass in the second and fourth quadrant, you always get negative codifference, and you can take linear combinations. So again, you can get very different things that have 0 codifference. Doesn't really have much to do with independence in any sense. So then, in going back for a second to the max stable world, you have this picans, in 2 dimensions you have a picans function, and there's very well known bounds that there's this envelope that any valid tail dependence function has to fit in this triangle. So you have the line 1 up here, and then you have the triangle here, and all valid tail dependence functions have to fall in that region. So an obvious question is there something similar to that in the sum stable law? And well, there is. I don't know. So I know what the upper envelope is. So so I'm calling these the envelope functions. First of all, it depends on alpha, which is not surprising. So if you let gamma, I'm asking how small can any scale function get? Call that gamma min. So pointwise, and gamma max. So the black curves, the solid black curves are the, what does it say? The max. So that's a proven upper bound, and it's sharp. It's achieved by particular cases. The dotted line you can't see very well is the independence case. When alpha is less than 1, the independence case corresponds with the maximum, the upper envelope. But when alpha is bigger than 1, it doesn't. And then the red curves, I don't know what the exact lower bound is. I have a conjecture. And we can show that that's actually reached. There's not a distribution that reaches it, but there's distributions that can reach at any point. I can construct a distribution that gets arbitrarily close. Convexity is not necessary here. You can, at least when alpha is less than 1, you can have a valid scale function that's not convex. Okay, so that's the probabilistic definition. Now we ask the question, if I have a sample, can I test for independence? So we're going to do something pretty obvious. So if I have a sample, now I don't know necessarily that it's normalized, so you can look at the marginal in the x direction, the marginal in the y direction, you get an alpha. They should be about the same. If they're not, you shouldn't be doing this process because it's not jointly alpha stable. But if they're about the same, easiest thing to do is to average those two as your estimate of alpha and use your scale function to normalize both components. So now I have a distribution that's approximately, that is normalized. And so what I'm going to do now is come over to this side, because I haven't been over on this side of the room. Pick some directions, so by picking angles theta 1 to theta m, and define the scale function. So I project the data in each of these angles, and I call that theta hat in the direction theta j. I'm sorry, not theta hat, gamma hat in the direction theta j, and these are going to be maximum likelihood estimates of the scale of the projected data set. So again, here's my original, this is my normalized data vectors. I project in this direction. And so for each of these directions, I do the projection, and then I do a univariate fit. So one of the advantages of this method is you don't have to really do anything multivariate. You do a sequence of univariate estimates, and then we're going to combine them. So this is the sample analog. Instead of looking at the integral, we look at this sum, and just for convenience, I'm going to take the case p equals 2. Okay, so these are my sample estimates of the scale in the different directions. These are the values of the independent case with our estimated alpha. Okay? Okay, so that's our test statistic. So geometrically, it looks something like this. I pick some grid points here, and I look at the difference here. So because things are pi periodic, you don't gain anything by looking at this piece, so we'll just concentrate in the first two quadrants. You've got to pick some grid points. A couple comments. First of all, we normalize things so the scale function is always 1 at these points. So it doesn't make sense to use that in here because I'll always get a 0 term. So to have a term that's always 0 is kind of silly. So what we suggest is using a uniform grid within the two quadrants, but excluding the 3 points at 0, pi over 2, and pi over 2 and pi. Okay, so we exclude the poles from this. And so this seems to be, from simulations, a reasonable way to do it. I'll discuss how many grid points to talk about we use in a second. You can pick other points, but if you're looking for sort of an omnibus test for detecting dependence, you kind of want to look in multiple places. It doesn't make sense to put the point math, the points, the directions we're looking at, and concentrate them over here. You'd want to sort of spread them out over the interval. So you get critical values for this test statistics by simulation, and the critical value is going to depend on alpha, the index of stability, the skewness parameters, so beta 1 is the skewness for the first coordinate, same for the second coordinate, how many grid points you chose, and the sample size n. So we did some power simulations to detect dependence, and there's a trade-off here. If you only do one direction in each quadrant, you have some power, but you can get more power to detect more kinds of dependence by spreading several points there. However, things sort of plateau. The power doesn't keep increasing as you add more and more grid points. I think it's just the fact that as you get points closer and closer together, you're getting less and less information. And in fact, we saw that in simulations about 5 points in each quadrant seemed to give you pretty high power. You didn't get much more than that after that. And then I'm not going to show you it, but there's actually, if you don't want to do the simulations, there's a fast approximation of the critical value based on a chi-squared distribution. So here's some power simulations. So down the left side is the sample size. Up across the top, we have the different cases. So the isotropic case, where the angular measure is uniformly is a Lebesgue measure on the circle. With small sample sizes, you have pretty low power. You're going to have to get up 300 or 400 or more before you have a lot of power in detecting that. If I take the independent case and I rotate it pi over 4 radians, so I put all the mass on the positive diagonal and negative diagonal, that's pretty easy to detect. Even with small sample sizes, you can do a pretty good job. If I rotate it less, it's not surprising that I'm closer to independence and you have less power and you've got to get larger samples. If I rotate it just a little bit, pi over 16, then it's fairly close to independence, and it's kind of hard to detect that. You're not going to be able to do that until you have fairly large sample sizes. On the other hand, if I take exact linear dependence, it's very easy to detect that. If I put all the mass on the diagonal, then when you look in the other quadrants, you'll see a big difference, and that shows up easy, even with very, very small sample size. So not surprising, things that are far from independent are easier to detect. Am I done, I think? Let me just show you one more slide here. So what if I have dimension greater than 2? So we can do this pairwise. So here's an example, artificial example, that generated a 10-dimensional data set. 3 of the components were strongly dependent, 3 of them were somewhat dependent, and the other 4 were all independent of each other. And then I randomly permuted the indices, and when you compute the scale function, you get a block. So here I'm doing color coding. The bigger the dependence measure, the darker I make it. And you see something like this. The nice thing is you can do some clustering techniques. So you just use the hclust function in R, and you can see this. And you clearly recover this block of 3 where the components were heavily dependent, this block where there's some mild sort of association, and then these independent terms. So this allows you to decompose a higher dimensional model. If you can find blocks that are independent, you can reduce the dimension, work on all them. And let me just put this up, and I'll stop here. You can just do something like an autocorrelation function. If you have a time series, a stable time series, you can look at different lags down here. You can plot this eta thing, and then again, since we can simulate this critical value, you have this idea of, again, you can try to get some idea. This is from a simulated AR1 process, and you can see the geometric decay here, but you can get some idea maybe of what order model to build. So I'll stop there.
Thank you, John.